This is my video report for lab4 oscillation. For this experiment, we had to analyze the motion of an object swinging in an arc, meaning oscillating in both x and y directions. While this motion is complicated but pretty similar to the motion of a mass oscillating just vertically on a spring, we'll be using the same techniques and fundamental principles to the ones introduced for a more simple case in the video lectures. So now let's describe the experiment in more details. The spring is attached to a fixed point, and initially the mass is in a static equilibrium. The values of the calibration lengths, time between video frames, and relevant masses are the same as the vertically oscillating mass discussed in the video lectures. The initial x and y coordinates are minus 0.128 and minus 0.704 meters respectively. The initial velocity is 0 meters per second. On this slide, I have described how to calculate using the techniques introduced in the lecture videos the oscillation period, stiffness coefficient, and the relaxed length of the spring for the vertically oscillating motion. You may pause the video now to look closely at the procedure. Here I have summarized the most important concepts used in the experiment: Newton's second law, velocity and position update equations, Hooke's law, gravitational and spring forces, and the energy principle. On the next slide, you can see the tracker analysis. I have plotted both the x and y relationships with respect to time t. You can see that the red mass points go in circles, almost exactly following the trajectory of an object. This has allowed us to obtain the coordinates through the whole experiment. Then we have copy-pasted this data into the Excel workbook and created the CSV file. This file is used in the GlowScript code to plot the experimental model. On the next two slides, I have inserted the screenshots with the edits I have made in the code. On the top two, you can see the initial conditions set it up. On the bottom picture, I have initiated the gravitational and stiffness constants, as well as a few other values. And here you can see the recursive loop where we calculate the energy changes, gravitational spring, and net forces. So when we compare the y position versus time plot of the two models, we can see the curves have the same qualities, frequency and oscillation period, and are pretty much identical in the beginning, but as time goes, they go out of phase due to the environmental and human error that affect the tracker model. The blue line shows the prediction motion generated in the GlowScript code, and the red one is from tracker calculations. Looking at the change in energy versus time graph, we can see how the energy principle is satisfied. The orange line represents the total change in energy, which is, as expected, nearly zero. And we say nearly because there is still a few factors such as human and environmental errors that affect the results. And finally, we can calculate the period of oscillation in two different ways, using either the x-coordinate versus time relationship or the y-coordinate versus time plot. Ideally, the two values have to match. However, we cannot exclude the human error, and the periods are a little bit different. So for the x-coordinate plot, we have obtained the value of 1.52 seconds, and the period from the y-coordinate plot is 163 seconds.